So now we want to introduce this notion of a dual space of a Banach space, and we want to eventually talk about the dual space of the LP space and L1 space and so on. And to do that, let's just do something a little bit extra. Let's talk about continuous linear maps between two Banach space. If you're going to take functional analysis, this is going to be probably the second half of your course, talking about all the properties of these linear maps. Okay, so I'll just get you prepared for that course. And also this is basis of the operator theory. So if you move on beyond functional analysis, you want to do operator theory. And that's basically you want to study the properties of these kind of maps. All right, so the basic setup is the following. Suppose we have two vector space V and W, and we put some norm. Let's put the norm and the subscript, this V and W, just reminds us which space we're on. And let's just assume for now they're just Banach space. So they are complete normed vector space. And given two vector space, we can talk about linear maps between them. Okay, so a map T coming from V to W is called linear. Essentially just a linear map. Okay, so let me remind you what linear map is. So suppose you have some combination of two vectors, say A times B1 plus B times V2, then everything is linear. So you can pull out a scalar. So this is A times T of V1 plus B times T of V2. Okay, so that's just the definition of linear. And in this course, our vector space or Banach space are over the reals. So the A and B are just scalar, so they come from the real line. And in fact, you can probably in functional analysis or later, usually you will look at a complex scalar vector space. So the V and W, they're vector space over the complex. Things are kind of similar. Okay, there's some technical difference, but everything works almost the same. All right, so the first theorem we want to prove is when is these linear maps are continuous. So let's show the following are actually equivalent. So this map, this linear map is continuous, actually, if and only if it's just continuous at one point. So let's just say continuous at point 0. And in fact, it's also equivalent to the following. So if I evaluate this map on some vector where the norm of this vector is bounded above by 1, so you can think about you evaluate the unit ball on the V space and by this linear map, then what you get is somewhat bounded. Okay, this T of V, the normalist T of V, is going to be bounded above by some constant less than infinity. So the supremum, we also denote this by the norm of T. So the norm of T, let's just define it to be the supremum of this one. Okay, so we'll say this is actually operator norm. I'll make the definition later. But actually, these three are going to be equivalent. Okay. So the proof, while 1 implies 2, is kind of trivial because, well, if you're continuous everywhere, you're certainly continuous at 0, so there's nothing to prove. Well, for 2 implies 3, let's assume otherwise. So if the supremum is not finite, okay, so think about what you can do, then essentially you can find a sequence, let's say Vn, okay, the Vn, the V norm are going to be bounded above by 1. And on the other hand, the T of these Vn will be unbounded, okay, so their norm will be unbounded, so they will diverge to infinity, okay, their norm is going to diverge. And because they're diverged, well, without loss of generality, let's just assume, well, first of all, let's assume Vn are non-zero. Well, because if Vn are 0, linear map will map 0 to 0, so we can just assume everything is non-zero. And we can also assume the T of this Vn, because they're diverging to infinity, so we can just say T of Vn is greater than or equals to n, okay? So if now we can basically just drop to a subsequence. Okay, this is kind of clear. All right, so if we have that, if you consider the sequence Vn divided by n, okay, so they are going to the norm of these will be less than or equals to 1 over n. Okay, so this Vn divided by n, that's clearly converging to 0 in norm in this vector space V, in this Banach space V. But if we evaluate T of this Vn divided by n, okay, so if I consider its W norm, well, T itself, first of all, is linear, so I can pull out the 1 over n. And the norm is also, you can pull out the scalar of the norm. It's a norm, all right? So that's equals to, you move the 1 over n outside, that times t of these Vn. But by our assumption, the t of Vn, we chose our Vn so that t of Vn is greater than or equal to n. This is the W norm, okay? So when you divide by n, that's going to be greater than or equal to 1, okay? So the point is not 0, okay? So what do we have? Basically, now we have a sequence of vectors converging to 0, but the t of this sequence of vectors is not converging to 0. Okay, so t is not continuous. Okay, so because here t of 0 is 0, that's just from the linear map of t, so t has to map 0 to 0. All right, so this proves 2 implies 3, and finally, let's show 3 implies 1. Okay, so suppose the operator norm is t evaluate on some vector less than or equal to 1. If that norm is bounded, then let's show it's actually continuous. And in fact, I want to show something extra. I actually show this t is Lipschitz, and so it's uniform continuous, so it must be continuous. All right, so let's take any x and y inside V. Let's just assume x is not equals to y. Okay, so I want to show the norm of tx minus ty is close enough when x and y are close enough. Okay, so let's consider tx minus ty. Well, first of all, because t is linear, this is just t of x minus y. Okay, so I can move them together. And now is t evaluated on a single vector? Well, this vector, the norm of this vector may be bigger than 1, but I can always normalize it by dividing its length. Okay, so what I can do is I can say this is essentially t of, let's multiply the norm of their difference, and then let's divide it. Okay, this is kind of a standard trick in linear algebra. And now this one thing here, the x minus y, I assume x is not equal to y, so this norm is certainly non-zero. So this is a scalar, okay? This is just a number, okay? Let me just label this is the W norm, and this is the W norm, and this is the V norm. The V norm is just a number, so I can, because t, again, is a linear map, I can pull out this linear factor. This number is also positive, so I can move it outside of the W norm, okay? So this whole thing will be equals to x minus y, the V norm, multiplied by whatever is in there. So this t evaluate on this vector, the normalized vector, x minus y divided by its norm. All right, so now if we look at what do we have here, so you have a vector divided by its length. So this is a unit vector. The norm of this is equal to 1. Okay, so the norm of this is equal to 1. So you're evaluating some vector with norm equal to 1. Well, you know it's going to be bounded above by the operator norm of t. Okay, so you have t times, let's move the, change the sequence. Okay, so it's less than or equals to the operator norm of t times the x minus y, the norm of x minus y. Okay, so let me copy down what we start. So we start with tx minus ty, and I show it's less than or equal to some constant. So this is a constant times the distance between x and y. Okay, so this is basically the definition of a Lipschitz function. Okay, so t is Lipschitz. And probably you already seen from 351 or even earlier, Lipschitz function are uniform continuous. So they're, of course, continuous. Okay, so t is continuous. And this is everywhere. All right, so this basically proves this equivalence. And so now let's just make some definition. So let's call t, it comes from V to W, is a linear map. Okay, so this is linear. Okay, and suppose it's continuous. Okay, then we call it a bounded linear operator. Okay, we call it a bounded. Well, sometimes you just ignore the linear. Well, usually you deal with linear maps, so you can just ignore the linear, but it's called a bounded operator or bounded linear operator. Okay, so this the norm of t, I already said this is called the operator norm. Okay. So again, if you have taken functional analysis, this probably a third of the last bit of the course is talking about these bounded linear operators. And let's just make another notation. Let's use this B from V to W. This is just the set of all these bounded linear operators. So all the T from V to W, where I can just say T is continuous or the operator norm is less than infinity. Okay, so this is just the set of all these bounded linear operators. Okay, so this set has a norm, and the next video we're going to show this is actually going to be a Banach space itself. Okay, but we'll leave it to the next video. So at the end of this one, I just want to prove one little thing. So I just want to remark. So once you know T is bounded, so this T, the operator norm, let's say less than infinity. So if you consider T of any vector V, okay, let's say V is non-zero, so V is non-zero, then you already seen this. You can normalize this V, so you can say, well, this is the norm of V, okay, in the V vector space, okay, and it's actually T value the normalized version of this V, so V divided by its norm is going to be a unit vector, okay, so it's going to be bounded above by the product of these two. Well, but the first one is bounded above by the operator norm, okay, so you have T times V, okay. So this inequality is going to be very useful, okay. So whenever you're dealing with a bounded linear operator, you often use this inequality, and you can notice if V is just zero vector, then this inequality still holds, okay. So we're going to use it in the next video.